So in the first sort of column there, I've got manifolds which have spherical metric. In the next column, I've got manifolds with a flat metric. And then what happens over here, everything else, will have what's called a hyperbolic metric. And for this, if you don't know what hyperbolic plane is, I'm afraid you'll have to just take it on faith. But the hyperbolic plane is, topologically it's a plane, but it has this negative curvature metric. The negative curvature, you can see a small piece of the hyperbolic plane like this, looks like a saddle. So when you sit on it, facing sideways, it's a saddle. And what's harder to imagine though is a surface which is saddle-shaped at every point. And in fact, you can't embed the hyperbolic plane in Euclidean space, so it really is hard to imagine. But if you can imagine that, that's what a hyperbolic plane is like. And it's a perfectly good differential geometric object. And every one of these surfaces can be obtained from the hyperbolic plane by quotient out by a group of isometries. And notice here, there are two ways of thinking about the torus. You quotient out Euclidean plane by the group of isometries, or take the fundamental region, you just glue edges together. And there are standard pictures of these surfaces too, which you do just that. So for the genus 2 surface, for example, there's this picture where you take an octagon. Should have done this, shouldn't I? But I think through that one, through that one.
Is it okay if I come to? Is it okay if I come to?
Notation is very poor, but anyway, you glue up the edge of this octagon and it turns into a surface. And this can also be viewed as an object in the hyperbolic plane as a fundamental region of a group acting on the hyperbolic plane by isometries and so on. So, but if you don't know that, to take it on faith, I'm afraid. So, in 2 dimensions, to summarize what I've just been saying, thinking differential geometrically, there are natural geometries on every closed surface, and you get spherical geometries here, flat geometry here, hyperbolic geometry, which is negatively curved here. So, something which is non-geometric, worth pointing out, I'll just erase, I'm afraid, make a comment. If you look at the Euler number of these two surfaces, this is 2, this is 1, the Euler number is positive. Here, the Euler number of the torus and the Klein model is 0. And here, the Euler number is negative. This exactly fits the trichotomy into geometries. These surfaces have this metric with positive curvature. These surfaces have this metric with 0 curvature. And these surfaces all have a metric with negative curvature. And the Gauss-Bonnet theory is what connects these three things. The Euler number is always going to have the same sign as the curvature when you have constant curvature. So this, by the way, proves that these surfaces cannot have flat metrics or negatively curved metrics. These, the torus and hyperbolic, cannot have positive or negative curvature metrics, and these cannot have positive or flat metrics, just by using the Gauss-Bonnet theorem, which says that if you integrate the curvature of the surface over the surface, you'll get 2 pi times the order characteristic. So if you don't know that, that's going to be my view. Okay, so that's a very nice situation, and of course this is extremely classical. I don't know how far back everything I've said dates, but a long, long way, long before I was born. So, but the question which Thurston raised, not right away, but in about 1980 maybe, was whether there's something analogous going on in 3 dimensions. And this was just a question that nobody had ever thought of, as far as I know. So let's talk about 3 dimensions now. So before I ask the question, let me start by just giving some examples, because it's good to have a few examples at your fingertips. It is, of course, obvious that there must be lots of free manifolds, but people often get stumped to actually produce very many. So let me just give you a good selection. Well, the first thing is there are lots of knots. I can't draw very many, but there's one. There are lots of knots, then you can bed a circle in a 3-sphere like that. And if you take its complement, you get an interesting submanifold in a 3-sphere. So the complement is an interesting manifold, and there's lots of them because there are lots of knots, but it's not quite what I want because it's not compact. Because if you take out the knot, what's left is an open subset of the sphere. What I'd rather do is look at what's called the knot exterior, where you take S3 minus the neighborhood of the knot. So I'll just draw the knot, unknot it for convenience. You just take the neighborhood, thin neighborhood, which of course is just like a donut, and you move the interior of that. What's left is a compact manifold with boundary and torus. And it is obvious that because there are lots of knots, there must be lots of these. Now, if you don't like having boundary, you can take two of these things and glue them together, and thereby generate huge numbers of closed manifolds. In some sense, these are not very generic, but I'll come back to that comment later. Now, there are actually some much easier three manifolds to think about, which are not really three-dimensional, just sort of 2 plus 1 dimensional. So the first obvious thing is to take a surface crossed with an interval, or a surface crossed with a circle. So these aren't really three-dimensional, so to speak, but they're obviously perfectly good examples. And this surface, you can make it compact, you can make it closed. Oh, actually, what's the example of that? And then you can get a bit more ambitious, and you can take twisted eye bundles. So instead of taking the product, you can actually give it a twist, so it's a bit more complicated. And here, I'll just leave that. I'm more interested in these objects here. I can take a bundle over the circle, with fiber F. What does that look like? I take F cross I, and glue the ends together by some homeomorphism, and now you've got a circle's worth of copies of the surface instead of just an interval's worth, and that's a bundle in the circle with fiber F. There are many homeomorphisms you can choose, so there are many such bundles. And you can also do the other thing. You can take a bundle over F.
And what was the one you wrote right under F squared cross I?
Sorry?
F
This one?
The one underneath.
Ah, this is red twisted.
Oh, okay.
That's all.
Okay.
But it doesn't matter because I'm not going to come back to that.
Okay.
So the bundle over F with fiber in the circle. That's a little bit harder to describe what you're going to get, but if you just think about a product, actually, you won't be too far off. And then there's one more generalization which I need to talk about. This is the Zipher fiber space, just very briefly. Talk about it. It's a very special class of free manifolds which were actually defined by Zipher in the 30s, so it's really a long time ago. Actually, he defined and classified them, which is very convenient. And they turn out to play a very crucial role in what I'm going to be talking about. So it's a kind of generalization of this bundle over fiber, over a circle with fiber S. So if I take a surface, F, I can triangulate it, say. So I just think about standard triangulation. Lots of triangles glued together. When I take a bundle over the surface with fiber, a circle, that means that above each point in the surface, I'm going to see a circle. And that, when you have a triangle, you're guaranteed to see just a product, a solid torus. So that tells me that my bundle here is actually equal to a union of solid tori.